Hello everyone. Today we will be presenting our evaluation of Reconformer, a deep learning based architecture for accelerated MRI reconstruction. In this presentation, we will walk you through the problem we are solving, how the model works, the changes we made to the code base to get it running, and finally the results we obtained. Hope you'll enjoy. Here's a quick look at how the presentation is structured. We will start by explaining why MRI acceleration is a problem in the first place, then introduce the reconformer method. After that, we will go over the code level contributions we made, followed by a short-lived demo. We'll wrap up with our visuals and numerical results and a brief discussion. MRI scans are inherently slow. This makes patients uncomfortable and can cause blurring due to the movement. One way to speed things up is to collect less data, specifically by undersampling a region called K-space. The problem is this shortcut breaks a fundamental signal processing rule and introduces severe image artifacts. So the challenge becomes, can we recover a clean, high-quality image from this incomplete data? Traditional deep learning approaches using CNNs have been tried, but they have a key weakness. They only look at small local regions at a time and miss broader patterns across the image. Reconformer tackles this by replacing the CNN backbone with a recurrent transformer. Unlike CNNs, transformers can capture relationships between distant parts of the image simultaneously, both in the spatial domain and in the K-space. The model is structured as an iterative, unrolled network, meaning it refines its output steps by step rather than doing it all at once. Crucially, each step includes a data consistency layer. This acts like a correlation mechanism that forces the model's output to stay faithful to the actual measurements collected during the scan.
To modernize the Reconformer repository, we refactored its core Fourier transform modules. We replaced deprecated PyTorch functions like torch.iftt and with the current of torch.fft standard using native complex tensors. This eliminated legacy bugs and optimized data flow for modern environments. Next, we built a custom evaluation pipeline to go beyond simple global metrics. Using a specialized visualization hook, we now extract and audit slice-by-slice outputs, including K-space data and error maps. We scaled this across 174 volumes on NVIDIA A100 GPUs for visual and statistical rigor. And for our live code demonstration, finally, we prepared a live inference workflow using an E-volume at a 4x acceleration factor. By applying a 1D Cartesian mask, we simulate real-world undersampled MRI scans. You will see the recurrent transformer efficiently suppress aliasing artifacts and restore fine anatomical details in real time.
Hello, welcome to our live project demo. Here you can see our Google Colab notebook. We first installed some libraries and cloned the official GitHub repository. Here is the inference setup. There is our dataset path. There is our weights path. So we will run the inference code for just one image. And this is the evaluation Python code. We changed these two functions in the code. And also in the transforms.py, we changed some FFT code for it to be compatible with newer versions of Python. So here is our Google Drive. So there you can see the dataset consists of a single H5 file, which consists of nearly 35 slices. Our results are empty. And now I am running the inference code on this single volume, which consists of 35 different slices, nearly 35. So it takes some time to load the weights, but after it loads the weights, the inference happens really fast. So we are on Google Colab. We use A100 GPU. So here you can see it started to download the weights now. That's the weight path. So then it instantly run the inference on the single volume we have. So as you can see, we have an STIM of 0.95 and a PSNR of 38. So this is relatively high compared to our entire dataset. Now let's see. We go on to the results from the Google Drive. So there you go. We have our reconstructed image. There are 35 slices here, but I mean, for it to be in the middle, let's look at slice 17. So this is the reconstructed image for slice 17. And now I'm gonna show you the original image as well of the same slice. So this is slice 17, original image. And let's look at the k-space mask that we used. So this is the k-space mask. Our acceleration factor was 4. So thank you very much. This was the end of live demo.
We show the qualitative reconstruction results for 4x and 8x acceleration. In the 4x case, reconformer suppresses aliasing artifacts very well, and the reconstructed image looks very close to the ground truth. The main anatomical structures are clear, and the error map shows only limited differences. In the 8x case, the reconstruction becomes harder because much less k-space data is available. The model still preserves the global knee structure, but the error map shows more visible errors, especially in high-frequency details such as fine textures and sharp edges. So visually, 8x is still usable, but it loses more detail compared to 4x. For slide 9, we support this with quantitative metrics. We evaluated 174 volumes and approximately 6,000 slices from the fast MRI validation split. We use NMSE, SSIM, and PSNR. The lower NMSE is better, while higher SSIM and PSNR are better. At 4x acceleration, we get NMSE 0.03, SSIM 0.81, and PSNR 32 decibel. At 8x, NMSE increases to 0.04 and SSIM drops to 0.76 and PSNR drops to 30 decibel. This matches the visual results. The 4x is cleaner while SX has more error. Still, even with the 87% of the raw data missing at 8x, the model keeps a reasonably strong SSIM, which shows that Reconfirm handles aggressive acceleration quite well.
Okay, so now to wrap things up, what worked well in our model? So there was a data consistency layer. We dealt with same mechanisms in the algorithms that we see in class as well. So that layer enforced measurement fidelity. Also, we have seen that transformer architectures are capable of capturing global artifact dependencies instead of CNNs, which only capture local dependencies. So for our limitations, at 8x acceleration, the model could not successfully capture high frequency artifacts due to 87% of the information being lost. And also the computational cost is extremely heavy. I mean, per volume, the inference costed around 8 to 9 seconds. So this is not very practical in a clinical sense. And future work may include integrating parallel imaging physics, like for multi-coil sense, some different algorithms. We only dealt with single coil measurements at this model. And so that wraps things up. Thank you very much for listening.